I'm going to start off by talking about the WASCoB research we had. This was all NREC funded research that we've done over the past 6 or 7 years. And first off, I want to thank all the people on the slide, because these grad students, they're the boots on the ground. If none of this, none of this would be possible without them. And then we got Amelia Vick on there, that's one of our researchers. So I'm going to talk about field to stream, the role of WASCoBs in Southern Illinois agriculture. So I'm sure everybody in here knows what a WASCoB is, but by definition, it's an earth embankment that goes across an ephemeral drain that will slow down the water and it's designed to, it's in the name, water and sediment control. So it's designed to slow down the water, let the sediment settle out, and then it's also, starting to catch on in terms of water quality, looking at nitrogen and phosphorus. So the purpose is to prevent gully erosion. That's the main thing, trap sediment and reduce storm flow. And then the application, obviously in these areas of rolling topography, it's not going to be a practice that you're going to put everywhere. So up here in central Illinois, not so much. But I think Lowell and I had the same introductory slides. It looks like we collaborated on things. But this is Illinois, and I just wanted to show you that this is not just a Southern Illinois problem. We've got WASCoBs, the star up there is in Menard County. So our first project, WASCoB 1 we call it, was up there in Menard, and that picture to the left is one of the concentrated flow areas that we were putting some of these WASCoBs on. So about 59% of the state's considered flat, and everything else is 2% slope or greater. And in those areas that are 2% slope or greater is where we're going to focus on putting these BMPs. So Illinois soils, as you all know, north central soils, they're typically the most productive soils in the state. They're flatter, they're deep, dark, organic rich soils with high fertility. And they have flat terrain here, so, except some of the terminal moraines from the glaciation. So things like tile management that we've heard about this morning, bioreactors, drainage water management, cover crops, all these things can be applied up here in this central part of the state. And then the WASCoBs are more applicable to the southern part of the state, but it does creep up the west side of the state. So if you look over here to the left side of Illinois, we got the Illinois River up here. We've got the Kaskaskia. So it's not just Highway 50 and south. It does creep up. And then on the east side, we have the Wabash and all the tributaries over there. So basically, this is a tile map, or potential tile map for Southern Illinois or Illinois. And you can see all the red areas. That's where tile is going to be most probable. So everything that's not red, that white, that green, that yellow, that's where we're going to talk about putting these WASCoBs, or potentially putting them. And I just want to reiterate that, we always talk about Illinois soils. We got the prairie soils, these deep, dark, rich, organic soils, and then we got what we call the timber soils. It's like the kind of the redheaded stepchild of the soils in the state. But I think Alabama, Texas, all those states in the South would be happy to have our timber soils, right? So they're still productive. We still got to protect them. We've got, all these pressures on the landscape now. We've got all the solar going in. We still got urban sprawl. So we're getting more and more pressure on our ag land that we still got to be considerate of these timber soils. So the importance of WASCoB from an erosion perspective. So we're looking at sediment, nitrogen, phosphorus loss, so water quality concerns. And then the other thing that I think's overlooked a little bit is the desynchronization of storm flow. So these things actually trap water from a hydrologic perspective, slow the water down, the retention time's 12 hours, but that allows all this other runoff. We saw Shalimar's 2.5-inch storm event and how quick that water was getting to the stream. So this just kind of desynchronizes it, lets it stair step down. It's not all reaching the stream at the same time. And then we had the NREC goals that we didn't quite reach, or the short-term goals in 2025. And so what they did, there's a rapid expansion of all the BMPs, putting them on the landscape, and WASCoBs was adopted in 2022 and as one of those BMPs. So they are important. So some of our previous and current research are the next few things I'm going to talk about, and we just call them, for the ease of this talk, WASCoB 1, WASCoB 2, and WASCoB 3. And WASCoB 1 was started back in 2018. It was the one up in Menard County. And then We had WASCoB 2 pick up in 2021, and it's finishing up this year, and then WASCoB 3 picked up in 2023, and it's going on for the next few years. So the objectives of WASCoB 1 were to look at WASCoBs versus no WASCoBs, so just an ephemeral gully compared to a gully with a WASCoB. And then we also incorporated a cover crop treatment in that one as well. WASCoB 2, we were looking at basin characteristics and how they drive water quality. And then also we looked at drone surveys and how applicable drones were in looking at elevation mapping. So can we look at sediment accumulation over time? And then WASCoB 3 is looking at basin amendments. So things like biochar, gypsum, and wood chips. And Kendi will talk about that. He has a poster over there that will talk about he'll talk about WASCoB 3. The other thing, we were looking at flow rates. So we would put a restrictor on the intake. So we'd have a full flow, we'd have a restricted flow, which was the normal flow, and then one that's even a slow flow. So how fast the water drains off. So our first one up in Menard County, like I said, we were looking at these ephemeral gullies versus a gully that we put the WASCoBs in. So they were built in 2018. And then we also looked at cover crops versus no cover crops. So we looked at cereal rye in this one. And I'll be up front with you. The harvest happened late one of the years, so we didn't really get a cover crop establishment. But the other year we had real good cover crop. The objective was to look at the cereal rye impact on water quality. And so how we sampled them, we had partial flumes, and that's the box on the left, looks like a bathtub. You'd put that in an ephemeral gully. The water free flows through it. It gives us a stilling well off to the left side of it that we can measure water height, so we can determine how much flow is coming through, so we can convert our concentration to a load. And then we also looked at ISCO automated water samplers. These are the grad students that go out in the field. They don't complain about anything. They just do their job. They sample water in the middle of the night, any time of day, on whatever setting you want to set it at. So the control structure is the other thing I didn't talk about, but to look at the outlet, so past where the tile drains, we had in the berm, we would have a control structure with a V-notch weir in it, and we had a pressure transducer in there to measure the stage of the water so we could see how much discharge was coming through these, again, to calculate that load of water. And then the other thing over here by this yellow precision tile riser is stacked pole samplers, and those are just designed to capture water as it increases in the WASCoB, in the basin. So that's kind of our incoming sample. Looking at the data, TSS did a really good job. One of the things that didn't do as good a job, and usually phosphorus is correlated, highly correlated with TSS, as you'll see in the other two projects, phosphorus didn't do as well. Nitrate is, in all three projects, was variable. So, it's in a dissolved form. They're not really designed for that, and I'm going to talk about some potential design modifications we can do towards the end of the talk that I think might help address the nitrate issue. And then WASCoB 2, we had 32 basins across the 3-county area, so down in Jackson, Williamson, and Randolph County. And we were looking at historic phosphorus, and then also water quality, a whole suite of things. And then we wanted to quantify the annual sediment deposition. So we did this in two ways. We used feldspar clay pads, and then also drones with just a camera, a 4K camera on it. The historic phosphorus, the 3-year average of accumulation was 0.9 pounds per acre per year, and there was a strong correlation, and this is the second WASCoB project, with TSS. So the overall driving factors that we saw in this study were basin slope was the most important thing. The first thing, we thought it was going to be buffer or WASCoB age, because we had them from established like year 1, year 7, out to year 20, and buffer or the WASCoB age really didn't impact it. It was more slope driven than anything. And then tillage and rainfall intensity were two other factors. Same thing you see with the sediment coming in to the WASCoB. Same thing, slope was the most important, rainfall was a positive correlation. And what we've seen in most all of our studies, these WASCoBs, it all comes down to timing. Like if you go in and till, or your land's fallow and you have a 5-inch rainfall event, which we had in July, we had another big one in June, when the field was fallow, freshly tilled, the vast majority of everything moved in that one event. Some of our WASCoBs almost, filled up with sediment, and I've got some pictures of those events in a little bit. So looking at the water quality, TSS, again, the best thing, water and sediment control. So 90% almost in terms of sediment. Phosphorus was up there a little higher this time, 63%. Nitrate at 16.5, and it's all over the board. DRP 20%, and then ammonium at 47%. And this is what our typical setup would look like. We were looking at inflows, water coming into the basin, and then outflows. So that bucket that's up on the stand has a little Milwaukee battery in it and a pump, and we pull a sample up when the water comes up in the basin. And then that's actually sampling out of the tile riser. So it's like a poor man's ISCO, basically. So those ISCOs that I showed you, all the 24 bottles, those are $6,000 a piece. So this is our economy version, or whatever you call that website, Temu or something that everybody buys things off of. So this is the version that we know how to fix. We've got somebody in-house that can fix these things and keep them up and going. But then we also had the stacked pole samples in there that show as the water, it takes a snapshot at 4 inches, 8 inches, 12 inches, and 18 inches. The other thing we looked at with WASCoB 2 was the feldspar clay pads. So this is just a real white, bright clay that you would sprinkle out on the ground. And if you have tillage, that becomes a problem. It would get incorporated, but sediment will come in, accumulate on top of that, and then you just take a soil core, push it through the clay pad, pull it out, and then you see that bright white line in that third picture over there that shows how much accumulation occurred on top of that sediment core. So we do this, and some of them we'd actually buried a big aluminum disc, a 3-inch disc, because when tillage was a problem and it was getting incorporated into the soil, we could always go back and find that disc and then run a pin flag down to the disc and measure depth on top of that. And we wanted to compare this to the drone flight. So Durga, she's got a poster over there, again, another plug. But she was looking at drone flights, so we'd go up, fly the drone on a pattern, and look at accumulation over time. We basically created a DSM, a digital surface model that paints a picture of what the surface looks like, and then we'd come back over time. It could be one event later, it could be a year later, and see how much accumulation occurred in that WASCoB. And so when you compare those two methods, looking at the feldspar to the digital elevation model that was created by the drone, the feldspar is accurate because it's an intact core. You're taking it, it's in situ. The drone, it has to fly multiple flights, and it could be a year apart. There's about a 3 to 5 centimeter difference between the two. So the drone's not quite as accurate, but 3 centimeters, we're talking 1.5 inches. From a vertical resolution perspective, that's not bad, but when you try to extrapolate that across a half-acre basin, that becomes a big mass of sediment. So not as accurate for short-term studies. So if I can start a GoFundMe site if you want to, and we can get a LiDAR unit, and that would be way better, but they're about $55,000 or $75,000, so we're going to wait on that one for a bit. WASCoB 3. So this is the one Kendi's working on. We got a 70-acre field right there on SIU Farm, so it's a perfect location so we can do field demonstrations, get people out to the field real easy. It's got a history of gully erosion, so you saw a lot of erosion on the field. It's a Hosmer silt loam with a 2 to 5% slope for the most part. And then we had an NRCS survey, engineer come out and survey the site, and we did 10 WASCoBs, so 10 different basins, and then 2 blind inlets. And this construction was completed exactly 2 years ago today almost. So the objectives of this one, like I said earlier, was to look at biochar versus gypsum versus wood chips in terms of amendments in the soil. The biochar was a hardwood biochar. The gypsum came from Prairie State, and the wood chips were more of a sawdust. And these were incorporated into the soil, so they didn't just wash off or float off. And then we wanted to evaluate modified WASCoB retention time, so the slow, the fast, and the normal drain. So NRCS would be considered the normal drain. We had one that sped up faster to get the water off quicker, and then we had one slow to retain soil, or to retain the water for a longer time. And then we wanted to look at crop yields as well, and then calculate the economic impact at the end of the study. So here's kind of what the treatments look like just from a visual perspective. The wood chips are on the left, and the black one's the biochar, and then you have the gypsum, and then the control is the empty one, so we didn't even have to put anything in that jar. And then the other three discs right there are just showing you how, the one on the left we don't use. Water wouldn't flow through that one. That's just what the restrictor plate looks like. Then we had one like a 3-inch hole. It kind of fluctuates a little bit because we're trying to get a 5-hour drainage time per inch of rainfall. All right, so they varied a little bit based on WASCoB's size, number of gallons coming through. The medium was a 3-inch per hour, or hour per inch of rain, and then the fast was a 2-hour per inch of rain. So again, the setup is about the same. We're looking at stacked pole samplers coming in, ISCOs going on the out, and then looking at nutrient loads and trapping efficiencies. And what stands out here are the red numbers. For TSS and TP, the slow drain outperformed the other ones. The gypsum and biochar weren't too bad on those. Nitrate, again, all over the place. And then DRP, the biochar was the best, with the slow drain not being bad. So overall, I think the slow drain was probably the best treatment to date. One of the things that we noticed, though, in the first few events, the biochar and gypsum did really well in the wood chips, and then it kind of started tailing off. So we're thinking, like, what's the longevity of this stuff in the soil? And Carl did a study on gypsum not too long ago, where it was about a year residence time in the soil. So do we need to reactivate them? How often do we need to put them in there? So Kendi came up with another study design looking at different biochar rates and in the field, and did a replicated design to see how long it stays based on soil sampling. He's going to come back and see how long it persists in the soil. So we need to reapply. We can do that. The yield impacts. Nobody's going to like this slide in terms of WASCoB. So if you're starting at the top left corner, it's 2022 pre-installation. Below that, and that's soybeans, and it looks pretty bad, doesn't it? So the WASCoBs actually flooded some things out in some of those years. And then the corn year, it was a real late planting date. It was like June 1, and those, because you know all the weather, we had wet and dry, wet and dry. It didn't get put in time, so those areas tended to be more weedy and more wet. So we didn't have really good yield in those. But I got some ideas on how to fix some of that too. Or not fix, but talk about it. So the summary across all three of these studies, we had 4 counties, 40 different WASCoBs we looked at, 7 years of data, 136 rainfall events, and anybody that's chased rain knows that's a lot of rainfall events, and these students were working overtime to get those, and we had 1,350 water samples. So the overall trapping efficiency, if we look at TSS, this is kind of all the different treatments, and I put a number in there, about 75%. Anything above that's green, that's good. So you see what falls out up there. And for whatever reason, it didn't come through on the slide. But slow drains up there. The 2 WASCoB from WASCoB 1, both of those were up there. So the cover crop treatments. And then on total phosphorus, the same thing pops up. Slow drains up there towards the top. And then with nitrate, much lower trapping efficiencies. Slow drain, again, probably, well, this one was actually weird. The fast drain showed up as a pretty decent one in terms of nitrate, which makes no sense. But it just showed how much variability was in that data in terms of nitrate. And then DRP, the slow drain, was the one way out to the right. So overall, load-wise, in terms of TSS, we had about 1,400 pounds per acre coming in. That's almost a ton of sediment. This is per event. This isn't per year, this is per event. And then total phosphorus was about 0.82 pounds per acre, nitrate 0.35, DRP 0.06, and then ammonium 0.07, so much lower. So some of the WASCoB challenges, I'm going to talk a little bit about some of the things we've seen and some of the things we've experienced over the years. By a show of hands, is this a farmer installed WASCoB system or an NRCS WASCoB? Let's say farmer. Who did that? Two of you? 3 of you? How about NRCS design? 0. Okay, so 4 of you participated in my survey. All right, that's good. That's typical survey results, right? Like 10%. It wasn't even that. But anyhow, so this was a farmer installed one. Why do you think it's farmer installed? They're in a straight line, right? It's easy to farm around. So if you're not going to adopt the practice, you're not going to do it. So it's got to be an adoptable practice. But you can see from where the concentrated flow is in that field, it needed some more in different locations. So design, like I said, farmer versus NRCS. Putting them out there is a benefit, regardless if they're farmer designed or not. Easiest versus best installation, and again, that's going to be how easy is it to farm around. The cost of installation, so there's a threshold. If you got the berm height versus the tile size. A bigger tile is going to cost more money. It's going to drain faster. Costs more money to put a bigger berm in, but you can get away with a smaller tile. So it's kind of right at that inflection point is where they're typically installed. And then that gets into the tile sizing, berm height, the number and position, where they go, and then the outlet type. So some other challenges. Just like every BMP we put out on the landscape, they got to be maintained, right? These riparian zones that have been out there for years have sediment built up at the front of them, but you can't go till trees under very easy. So we got to come up with a strategy to maintain these. We've seen crushed tile lines, plugged risers. They turn into great duck habitat. You got to clean these things out, and then you can have overtopping like the picture in the bottom left. So if the berm wasn't high enough, some of these extreme events tend to go around it and really doesn't function like it's supposed to. So some potential design modifications that we want to look at. Like I said, we installed 10 WASCoBs out on SIU farms. 6 of them are being used right now, so we're in the process of designing some different types of structures that actually siphon off the top instead of pulling from the bottom like a typical precision or a Hickenbottom. They're going to siphon off the top to allow more settling. And we're even thinking something more slow, because if you got a yield loss anyhow, we might as well keep the water in there for a little bit longer. I know it's not perfect if another storm's coming behind this storm, but if you can keep it there, you might start seeing some denitrification occur in those instead of over a 6-hour drainage time. And I think that was the video that probably won't play, but this is just another type of structure looking at the bell-type siphon. So something that floats up and down that will be able to pull the water up from the top, and it fluctuates with the height of the water in the basin. So we obviously need something that's going to automatically purge itself or start that siphon. So looking to the future, we got Abigail sitting over here. She's going to do a project on concentrated flow paths. So these are basically these ephemeral drains we've been talking about. Do we put a WASCoB on it? Do we put a grass waterway on it? Do we till it under? What do we do? What's the management practice for it? So on SIU farms, we've went out and she sampled all these different concentrated flow paths through aerial surveys, and then ground truthed them, took some measurements. But what we're seeing is about 82, and that's on the next slide, 82 to 100% of the fields are drained through these concentrated flow channels. This is what they typically look like. So think about the water coming off the field in terms of sheet flow. What's the buffer do? It settles, it slows, it allows that sediment to settle, and that settling sediment creates a berm. And that berm's usually at the front of the buffer. If you're getting over bank from bank full discharge, sometimes that berm gets positioned further back in the buffer. But water will travel along the face of that now and then find a concentrated flow path and break through, and it's a bigger problem. And you can see the elevation change on those in that graph to the top right. And these are the fields that Abby surveyed, and like I said, 82 to 100% of the fields assessed were drained through concentrated flow paths. So it's a dominant flow mechanism, at least in southern Illinois, and I'd say it goes right up that Illinois River up in here to central and northern Illinois. where sheet flow is not the dominant mechanism coming off these fields. So, like I said, she took the drone out, surveyed them, and some of them will go back with a total station and survey them a little bit more accurately to get like cut and fill volumes to see how much was eroded, how much sediment was lost. And then recently we designed a new apparatus. We're into these $150 range sampling equipment. So this is just a PVC pipe, but it has a LiDAR unit in there that shoots a float in the bottom that raises and lowers and trips this so it will sample CFP water. And then, like I said, we want to know what it's going to do. Is it WASCoB, grass waterway, tillage soil rehabilitation, or a buffer strip of some sort? So last thing is tweaking the, I'm getting close, right? You got time. I got time? All right. So I say tweaking the SMZ, or tweaking the streamside management zone. So pollinators is a big thing. It's going to continue to be a big thing, I think. What happens if we plant some in these buffers? And I just got done saying there's concentrated flow going through all the buffers, so why does this make sense? But we can talk about grass waterways and other places you have grass margins along the field to put some streamside pollinators and see what they do in terms of water quality. And then another idea we had was bees, bales, and buffers. So if a farmer has cattle and wants to produce hay on some of the grassed areas, that will actually remove some of that nitrogen or phosphorus from the site. A 1,200-pound bale on average has about 21 pounds of N in it and 5 pounds of phosphorus. So my take-home messages, like I said earlier, they must fit the operation. The BMP must be adopted to work. It's got to be economical. There's got to be a cost. There's got to be a benefit. You know, if we're putting hay out there and we can recoup some of that land that we take out of production, that's even better. And then we want to focus on keeping the soil and nutrients on the field. We want to target the most vulnerable fields, right? And then no single practice. There's no silver bullet. We got to start considering, I think, and I heard it earlier this morning, the word integrated BMPs. So I know early Shalimar said a 42% in terms of cereal rye cover crop. That could be part of our nitrogen, addressing our nitrogen loss in some of these WASCoBs before it gets to the WASCoB itself. So I think there's a lot of infield and edge of field different practices that we can start looking at together. And this, just again, want to acknowledge the Illinois Nutrient Research and Education Council. McIntyre Stennis helped with Abby's project, getting the preliminary data for the CFP stuff. And then, you know, we had some NRCS engineers come out, private landowners, all the folks. And then this is just a picture showing the dedication of our grad students. When it's time to get a water sample, they swim. And then we have Kendi, you know, he puts on his winter gloves at about 40 degrees now because he had a problem with one of the, I guess you got frostbite, or pretty close to frostbite if not. So the winter gloves come out early with Kendi. But that's all I've got, so if you have any questions, I'd be happy to take them.